Well, hello everybody, and welcome again to the University of Washington's Spring Astrobiology Seminar Series, and a special welcome to our VideoCon participants. Our speaker today is Dr. Jeremy Bailey of Macquarie University in Australia. Jeremy received his BA in Physics from Oxford University in 1995 and his PhD in Astronomy from Sussex University in 1978. He spent a large fraction of his career at the Anglo-Australian Observatory in Sydney, which is where I first met Jeremy while I was working on my PhD, and I think Jeremy was there for over 20 years. But more recently, from 2001 to 2007, Jeremy served as the Associate Director for the Australian Centre for Astrobiology and also as an Associate Professor of Astrobiology from 2005 to 2007. He is also, in his spare time, a member of the Anglo-Australian Planet Search Team, which has discovered 29 of the currently known exoplanets using radial velocity technique. Jeremy's interests in astronomy have been very broad, ranging from cataclysmic variable stars through induction, I guess, of molecular homochirality in star-forming regions to, most recently, terrestrial planets in our own solar system and extrasolar planets. However, Jeremy's diverse research has always been linked by his strong interest in the development and use of both infrared and polarimetric instrumentation. So today, Jeremy will enlighten us on how to use polarization techniques to detect and characterize extrasolar planets.
Yeah, thanks, Vicky. So the basic idea of using polarization with extrasolar planets is that sunlight is essentially unpolarized. In fact, we know that it's unpolarized to a very high level. The polarization of the sun has been measured to be less than around 1 part in a million. But when that light scatters off a planet, such as the Earth, it's polarized by a number of processes. So scattering off molecules, Rayleigh scattering, produces very high polarizations that peak at a 90-degree scattering angle. Scattering off particles, such as cloud droplets, aerosols in the atmosphere, also produces polarization, somewhat lower levels, 20% or less. And the variation of this polarization with angle, what we call phase angle, which is the angle between the sunlight and the direction it comes off, provides some information on the size and composition of those particles. So there's a number of ways that polarization can be applied in the study of exoplanets. And I'm only going to talk about some of them here, the ones that are highlighted here. Polarization can be used as a differential technique to help to pick out the planet from the speckle noise that you get around a star. And this applies to techniques that are being developed for looking for extrasolar planets with large ground-based telescopes, where they're using adaptive optics systems to sharpen up the light from the star and make it easier to pick out the planet. But you still get adaptive optic systems are not perfect, so they still leave a halo of light around the star, and you're trying to pick the planet out of that halo. And polarization is one differential technique that you can use to do that, because the light of the planet should be polarized, whereas the starlight won't be. And so many of these instruments are incorporating polarization systems. You can also use polarization to try to detect the scattered light from unresolved planets. Thinking here of hot Jupiter type systems, these are the planets that are being found in Doppler and transit planet searches, where you have a giant planet very close to its star, orbiting in a period of a few days. And at the moment, we have no hope of actually being able to resolve the planet from the star with any reasonable technique. All we can do is look at the combined light of the planet from the star, but it might be possible to use polarization to pick out the fraction of light that's coming from the planet. And if I have time, I'll say a bit more about that at the end of this talk. The main part of the talk is going to be about using polarization to characterize the atmospheres, particularly of terrestrial type planets. And we can use polarization in a number of ways. It can help to distinguish between clear and cloudy atmospheres. It can help us to measure the atmospheric pressure. It can help us to determine the composition and size of cloud particles. And one of the things we're particularly interested in is looking for liquid water. And there are ways of using polarization to look for liquid water, both in the liquid water droplets in clouds and liquid water on the surface of a planet. And all these things are hard to do with spectroscopy. Polarimetry provides information that's very complementary to what you get out of spectroscopy. It's also, in fact, possible to use polarization itself as a biosignature. You can, in principle, detect circular polarization effects due to light scattering off chiral molecules in, for example, in leaves or cyanobacteria, where you have chlorophyll. There will be a circular polarization signature of that light that's a result of the preference for one-handedness, the chirality of the molecules. And, for example, Bill Sparks at Space Telescope Science Institute is looking at such effects. But they're very small, and they're way beyond what we can think of doing on exoplanets at this stage. Okay, so the current status of extrasolar planets. So we now have 287 extrasolar planets known, according to the Extrasolar Planets Encyclopedia. Most of these have been detected by the Doppler method. That's looking at the varying radial velocity of the star as the planet moves around it and causes a wobble of the motion of the star. Quite a number now, and this is something that's increased very recently, is detection by the transit method, where we see the planet passing in front of the star, and those transit planets are very useful because they get, we can actually use the transit to get information on the atmosphere of the star. We now have 6 planets detected by the microlensing method, and this is where we see the planet passing in front, the star and the planet passing in front of a more distant star and causing gravitational lensing of the star. And you can get a characteristic curve which allows you to deduce the presence of a planet. And then there's 5 detected by direct imaging methods. These are mostly planets around very young stars, so the planet is still young and still producing light through its own heat. So most of these current detections are giant planets. Most of them are masses of hundreds of Earth masses or more, comparable to Jupiter and Saturn in our own solar system. There's a few lower mass planets found. The lowest so far found are down to about 5 Earth masses, and these planets are sometimes called super Earths. They could be large terrestrial planets rather than gas giant planets. Almost all the current detections are indirect detections. We are not seeing the planet itself. We're deducing the presence of the planet from its effect on the star. There's a few direct detections, and they're all by means of the thermal emission. And so the Spitzer Space Telescope has been used to detect the direct emission from some of the transiting planets. And there's also these near-infrared imaging observations of planets around young stars. Again, we're seeing the thermal emission, but no extrasolar planet has yet been seen by the light reflected from its star. And we have yet to find anything else like Earth orbiting another star. We don't have the sensitivity in most of these methods to detect a planet of Earth mass, although that should become possible soon with space missions such as Kepler, which will be capable of detecting Earth-like planets by the transit method. Nevertheless, there's a number of proposals for missions to directly detect terrestrial planets. This is very hard because a terrestrial planet is an extremely faint object. It's probably fainter than anything astronomers have yet measured, and it's sitting next to a planet which is 10 billion times brighter. So these are pretty challenging observations, but a number of methods have been proposed. So these 2 instruments, this is Terrestrial Planet Finder-Imager, interferometer, and this is Darwin, which is a similar proposal from the European Space Agency. These involve a number of infrared telescopes flying in formation and combining their light, and they can use interferometric methods to get rid of the light of the star and reveal the planet at thermal infrared wavelengths. And then an alternative approach is what's called TPFC, Terrestrial Planet Finder-Coronograph, and this is a large optical telescope, but working at visible wavelengths and using a technique called a coronograph, an optical system to get rid of the light of the star and again reveal the planet at visible wavelengths. It's actually TPFC and similar instruments that are most interesting for what I'm going to talk about here, because it's only TPFC that is looking at light reflected, starlight reflected off the star, and that's where we get the polarization effects. So all of these missions aim to detect and characterize extrasolar terrestrial planets, and the primary tool for planetary characterization has usually been spectroscopy in most of these proposals. What I want to point out here is that spectroscopy doesn't tell us everything we would like to know about these planets. What it basically does is allows us to detect some, but not all, of the gases that are present in a planetary atmosphere. And I want to explain here what we can do by including polarization in such a mission, and that can give us additional information. So these are some models of what the spectrum of a terrestrial planet might look like observed with one of these missions. So this is actually the infrared region up here showing what TPFI or Darwin would see, and that shows absorptions due to CO2 and ozone and water. And in the visible region, the region that TPFC would look at, you can see absorptions due to oxygen and ozone. So oxygen and ozone are biosignatures because they're produced in the atmosphere of the planet by photosynthesis. We can also see water vapor in this region and CO2 in the thermal IR. But there's a number of things we'd like to do that spectroscopy can't do for us. One thing it can't do is detect liquid water. And liquid water is the defining characteristic of a habitable planet. And the mantra in astrobiology in the solar system has been follow the water. Water is the one fundamental characteristic required for life. And so you want to look for liquid water to detect planets that are promising for life. We can't do that with spectroscopy. Another thing we can't do very well is detect the presence of clouds. And all planetary atmospheres in the solar system have clouds of some sort. And that means we can't really tell if the light we're looking at is coming off a planet's surface or coming off the cloud tops. And so anything we measure about the planet, we don't really know if it's telling us anything useful about the planet's surface. So for example, if we look at a planet like Venus, the conditions at the cloud tops are very different from those at the surface of the planet. Another thing we can't easily get at is the atmospheric pressure, and that's because we only detect some of the gases in the atmosphere. Some important gases, in particular nitrogen and hydrogen, which are the main components of the atmospheres of hydrogen in the case of the giant planets, nitrogen in the case of Earth and Titan, for example, don't have any spectral features at the TPF wavelengths. So if we're not seeing all the gases, we can't get an idea of what the total atmospheric pressure is. And that means we can't even measure the concentration of the observable gases properly, because they're affected by the amount of pressure broadening by these gases we can't see. So for example, the CO2 absorption features in the Earth and Mars atmosphere are actually roughly the same strength, even though Mars actually has a much bigger column of CO2, but in the Earth case there's lots more pressure broadening due to nitrogen, which brings the lines up to the same relative strength. And polarization can help us to do all of these things. And what the measurement we want to make is polarization as a function of phase through the orbit. So the features we're going to use to get information out of planetary atmospheres are the three that are illustrated here. They're all very familiar phenomena on Earth. So rainbows, which are due to scattering of liquid water droplets, glint of light reflected off a water surface, which is a possible technique for looking for oceans, and Rayleigh scattering, which is simply light scattering off molecules. It's what causes the blue sky. All of these phenomena, if you looked at them through Polaroid sunglasses or any polarizing filter, you will see that all of these are very highly polarized. And that's how we can detect them polarimetrically. So I'll start by talking about rainbows. Rainbows are caused by light scattering off spherical water droplets. And what we have is the light passing into the water droplet, reflecting off the inside of the water droplet, and then coming out at a different angle. And the light actually scatters through different angles depending on where it's coming into the droplet. So this impact parameter, which measures the distance from the center of the droplet. But if you plot those angles as a function of impact parameter, you find that there's a minimum scattering angle where these curves turn round, and there you get a pile up of light coming out at these particular angles. I'd better explain these terms, phase angle and scattering angle, because I'm going to use them a lot. So we have light coming in from the sun, reflecting off or scattering off a particle, and the phase angle is just this angle measured from the direction the sunlight's coming from, and the scattering angle is the complement of that, 180 degrees minus the phase angle. And observers always use phase angle, and scattering theorists always use scattering angle, so I'm afraid I'm going to have a mixture of the two, but they're measuring essentially the same thing. And for rainbow scattering from water droplets, the scattering angle is about 140 degrees, the phase angle is about 40 degrees. So this is what rainbows look like, and I've exaggerated the contrast a little on this picture to show up the effects. So you get the circular rainbow, that's the 40-degree angle around the anti-solar point. You get the coloured primary rainbow, and the region inside this rainbow is not dark. There's light scattering at all these angles, as well as the actual rainbow angles, but we only actually see the colours at this turnaround point, at the minimum scattering angle the light can reach. Whereas this region here is actually dark. There's no light scattering off the water droplets into this region, and then outside the primary rainbow you get a secondary rainbow, and you get another bright region here, and that's light that reflects twice inside the water droplet.
It's a caustic then?
Yes, that's right. Yeah. So rainbows are very highly polarized. These are photographs through polarizing filters and through so the polarization is in this direction, and in this direction the rainbow just disappears. There's essentially nothing comes through. The level of polarization of a rainbow is actually about 96% for large water droplets. Now the rainbows we're actually interested in for looking at exoplanets are not the familiar coloured rainbows that we see, which are rainbows coming off essentially raindrops, large water droplets, a millimetre or bigger in size. But you also get the rainbow phenomenon persisting for much smaller droplets. And in particular, what we're interested in is cloud droplets. Because when we look at a planet from outside, we're generally not going to see the raindrops because they're underneath the clouds, but we do see the clouds themselves, and the clouds are water droplets, but they're just smaller water droplets, typically about 10 microns in size. So with what happens with small droplets is you still get a rainbow, but diffraction effects broaden out the scattering peak of the rainbow. So if you could see one of these, sometimes called a fog bow or cloud bow, it's not actually coloured because the smearing of the light essentially smears out all the colours, but they remain highly polarised. And so if you look at a planet with clouds from a distance, there should be a peak in polarised light at this rainbow scattering angle, about 40 degrees for liquid water. To study these small particle rainbows, you can't really use the ray optics approximation that I showed earlier. We use methods such as the Lorenz-Mee scattering theory, and which models the scattering from small spherical particles, and there's a associated T-matrix theory which we can use for non-spherical particles. So from these we can calculate what's called the scattering matrix, which contains one component of this is the phase function, which is simply the fraction of light that gets scattered into each possible phase angle. And there's another component which describes the same thing, potentially for linearly polarized light, so how much linearly polarized light is scattered at any one angle. And the ratio of those is the degree of linear polarization. So I, for example, use Fortran codes from Mishenko to calculate these. I'll show a few plots as to what these look like. So this is just the phase function, the amount of scattered light as a function of scattering angle. And you can see essentially the same features that I showed in the photograph of the rainbow before. So here's the primary rainbow. There's light inside the primary rainbow. There's this dark region, and then the secondary rainbow. And if you actually have particles of almost the same size, you get these things called supernumerary bows, which appear inside the primary rainbow. They tend to smear out somewhat if you have particles of a broad distribution in particle size, but you can still sometimes see this supernumerary rainbow effect inside a rainbow. So this plot just shows the effects of particle size on the rainbow. So as the particles get smaller, I've started at 100 microns here, what happens is the width of the rainbow peak broadens out, and eventually it starts to shift to larger scattering angles. So this is the phase function, the total intensity of the light, and this is the polarized intensity. And they're on the same scale, so if the polarized intensity is the same height as the phase function plot, then that's essentially highly polarized light. And one of the things you can see is that as you get down to small particles, you start to see this feature at around 180 degrees scattering angle, which that's actually a related optical phenomenon called the glory, which occurs at this angle. And as you get to small particles, the rainbow and the glory sort of more or less join together, and there's light at all wavelengths, at all angles between the rainbow peak and 180 degrees. But if you look at polarization, you still get a well-defined rainbow peak going down to quite small particle sizes. It broadens and shifts, but there's still a fairly well-defined peak in these small particle sizes. Typical cloud particle sizes range from about 3 to 30 microns. So the average size, the global mean is actually about 11.4 microns, so it's close to this 10 micron plot here. So this is the sort of rainbow peak you would actually get from cloud particles. Now the angle at which you see that rainbow depends on the refractive index of the liquid. So I've shown here the rainbows calculated for 3 different liquids that we know occur in clouds within the solar system. So water at the top, this is sulfuric acid, which is what we get in the Venus clouds, and this is methane, which we get in clouds in Titan. And you can see that you could clearly distinguish these liquids from the shift in angle at which the rainbow occurs. These plots show the effect of particle shape on the rainbow. So you get nice rainbows with spherical particles, but as soon as the particle shape deviates from a sphere, so these are spheroids with different axis ratios, the rainbow peak rapidly disappears. And these are some different shapes: oblate and prolate spheroids and cylindrical particles. And so rainbows are a very distinctive indicator of spherical droplets. And spherical, in practice, in most practical conditions, means you must be looking at a liquid, because a liquid naturally forms a spherical shape because of surface tension. And then the other thing you need to get a rainbow is it has to be a transparent liquid. So this is the effect of putting some absorption into the particle, and that also causes the rainbow to disappear. And that means that if you actually looked at the spectrum of this rainbow scattered light, you could see absorption features due to the liquid that caused the rainbow. The best place to look for that for a water rainbow would be at about 1.95 microns, which unfortunately is outside the wavelength range of any of the TPF missions. So to summarize the properties of rainbows, they're generated by scattering from spherical particles. Any small departure from sphericity inhibits rainbow production. They're present for sizes down to about 1 micron, which covers all the clouds particles that we know about. They're highly polarized, and for small particles they're better defined in polarized light than in total intensity. The peak scattering angle is a measure of the refractive index and can help to tell us the nature of the liquid responsible for the rainbow. And any absorption in the particle inhibits rainbow production. And that means that rainbows are a very strong indicator of the presence of liquid droplets. So, in natural conditions, the only way we're going to get a spherical particle is due to surface tension, which causes a liquid to form spherical droplets. And solid particles are very unlikely to produce rainbows in natural conditions. All the solid particle aerosols that we know about in the Earth and other planets' atmospheres would have conditions that would prevent the formation of a rainbow due to non-sphericity, small size, or absorption, and in most cases a combination of these effects. Okay, now the models I've shown you so far are single scattering models, so they just look at what light scattered once off a water droplet would do. What we're looking at in a realistic atmosphere is a multiple scattering situation, so light can scatter many times off various particles before it finds its way out. It turns out, though, that the effect of multiple scattering is mostly to remove polarization. So the polarized light you see from an atmosphere is mostly going to be due to light that has actually single scattered, that's only scattered once off droplets at the top of the clouds. And there will be diluting light coming from multiple scattering cases, which can be considered, to a first approximation, to be unpolarized, and so it just dilutes the polarization. So it actually means that these single scattering curves are pretty much what you would actually expect to see from the polarized light from an atmosphere, except that the degree of polarization will be reduced because there's this diluting, unpolarized radiation. And you can see this is an actual multiple scattering model of rainbows off water clouds, and the shape is pretty much the same as the single scattering polarization that I showed in one of the earlier plots, which is shown up here. You can also see that in the multiple scattering case, the rainbow shows up very clearly in polarized light, but is a relatively weak feature in the total intensity of the light. So polarization is really the way to look for these things. Now, just to show that this actually works, that you can look at a planet from space and see rainbows, these are some observations from an instrument called POLDER, which is Polarization and Directionality of Earth Reflectances. This is a French-built instrument. That's the first version flew on a Japanese satellite called ADIOS, and there's a second version now operating on a microsatellite called Parasol. And this is an instrument that looks down at clouds from Earth orbit. It's about 800 kilometers altitude, and it looks at this phase curve of reflection from clouds. And the basic aim of POLDER, at least of the polarization part of POLDER, is to distinguish between liquid water clouds and ice clouds, and it does this very clearly. So red is a liquid water cloud, and it produces a nice polarized rainbow curve, just like the ones I've shown you. And the blue is scattering off ice clouds, and it's completely different. There is still some polarization, but the curve is completely different, and there's no sign of the rainbow feature. So that shows you can really see these things looking at the Earth from space. And then the other good example is that they've been seen from the planet Venus. Polarization of light from Venus was first detected by Bernard Leo back in the 1920s, but for a long time it wasn't fully explained. And the explanation was largely due to the work of James Hansen. This is the James Hansen who went on to be director of the Goddard Institute for Space Studies and the leading advocate for action on climate change, climate modeler and so on. He started by working on Venus, and he came up with the explanation for the polarization in the Venus atmosphere. And this is the polarization phase curve of Venus, observations here and Hansen's model And what we see is a primary rainbow here. This peak, which is actually, for Venus, is about 20 degrees phase angle, is just the same rainbow scattering effect that you get from water droplets, but it's shifted from 40 degrees, where we see a water rainbow, down to about 20 degrees. And that's because the liquid in this case is sulfuric acid. It has a much higher refractive index, and also because the particles are very small, and the small particle also causes a shift in the rainbow position. So from this polarization phase curve, it was possible to work out that the cloud particles were spherical droplets, radius of 1.05 microns, and the refractive index was measured to be 1.44 with considerable accuracy, and the only possible liquid consistent with that is essentially concentrated sulfuric acid, so 75% H2SO4, 25% water. So this shows that looking at the total light of a planet, we can see a rainbow signal, which tells us about the liquid components in the atmosphere. Now, I've tried to work out what the total rainbow signal from the Earth should be if we were looking at the integrated light of the Earth. And I'm basically modeling it as combined from three components: clear sky regions where we won't see any rainbow signal, liquid cloud regions that will show a rainbow signal, and ice cloud which won't show a rainbow signal. And I'm using a couple of different models of what the typical global cover of these three components is. Total reflectance from the work of Giannetti et al., and the polarized reflectance from the rainbow according to the multiple scattering models I showed earlier from Golub et al. And if you combine all this together, you get a global signal of something between 12.7 and 15.5% for the two different cloud models. If the Earth was totally cloud covered, you get a 20% signal. So these are reasonably large polarizations that should be possible to observe. Okay, now rainbows tell us about liquid water, but liquid water in the atmosphere. And what we really want to know about is if there's liquid water on the surface, because that's really the defining characteristic of a habitable planet. There is a way of doing this using polarization, and that's using what's called glint. So simply sunlight glinting off water, and water is actually not very reflective under most conditions, but you do get this glint off water, which occurs for light that's actually reflecting at the specular reflection angle. So angle of incidence and angle of reflection the same. So these are some actual photos of glint spots off water through two different polarizing filters, and you can see there's a big difference. This light is highly polarized, not quite as high as the rainbows, but typically 70 or 80%. And you can also see the pattern of the glint depends on what the wind's doing to the surface of the water. It changed between these two cases in a minute or so. Now this is a photo of the Earth from space, and you can see the glint spot there. It's clearly visible, but you could also see that it's not going to be easy to observe this in the total light of the planet, because there's a lot of other light coming from clouds around there, which is going to dilute any effect of the glint signal itself. These are some models of the glint effects from a recent paper by Williams and Gaydos. And these show the polarization here and the total intensity as a function of phase angle. And these are models of this. So this top model is a model for a completely ocean-covered Earth with no clouds, and that's a favourable case for seeing glint, because the oceans themselves are largely dark and the glint spot bright. So you can get a strong polarization peak here. It's going up to about 70% polarization, and And where you tend to see the glint best is at crescent phases, and that's simply because the total light of the planet is reduced relative to the glint spot. The glint spot is a larger proportion of the light coming from the planet. This is a case where Earth geography has been added, so it's got continents as well as the ocean, and the continents are brighter than the ocean. So you get a much smaller glint polarization now, about 30%, and it's shifted over to smaller angles, more extreme crescent phases. And what hasn't been modelled here is what happens if you add clouds. And that's the real problem, because clouds are brighter than both oceans and continents. So if you put clouds into the model, this peak is going to get smaller, and it's going to get shift further to more extreme crescent phases. So glint is certainly potentially a way of detecting oceans, but I think it's actually quite hard to do in practice, at least for a realistic planet like the Earth, where you've got the glint spot competing with reflection from clouds and continents. The other feature that produces polarization in these atmospheres is Rayleigh scattering. And Rayleigh scattering is just scattering off molecules in the atmosphere. So just a clear atmosphere without any clouds will produce polarization due to Rayleigh scattering. And Rayleigh scattering is blue. It's what makes the sky blue in the case of the Earth. So it's seen best at short wavelengths, and it's also seen best at phase angles of about 90 degrees. Now you can see Rayleigh scattering without polarization. So if you have a spectrum of the Earth, this rise at the blue end is due to Rayleigh scattering. If you have enough of it, you may be able to pick out Rayleigh scattering on that basis. But you can do it a lot better and more convincingly if you measure the polarization. This Rayleigh scattered light is highly polarized, so Rayleigh scattering is polarization is a very strong signature of Rayleigh scattering. And this is the Venus phase curve that I showed earlier. Here's the rainbow, but the bit we're interested in now is this peak at 90-degree phase angle, which is Rayleigh scattering polarization. And you wouldn't be able to pick out a spectral rise to the blue in the case of Venus, because there is much less Rayleigh scattering going on than in the case of the Earth. And in fact, there are absorbers in the Venus atmosphere which absorb in the ultraviolet, which would actually bring the spectrum down, so you'd be competing with that. But in the polarization curve, you can clearly see the signature of Rayleigh scattering. And what you can measure from that is an estimate of the total atmospheric pressure. And that's because unlike spectroscopy, where we're only seeing some of the gases, all the gases in the atmosphere contribute to Rayleigh scattering. So the amount of Rayleigh scattering allows you to tell the atmospheric pressure. Of course, in a case like Venus, it's the pressure at cloud tops that you're measuring. You can't obviously see below the cloud tops. So a combination of these three effects, the glint, the rainbows, and the Rayleigh scattering, can tell us quite a lot about the atmosphere of a terrestrial planet and even the surface. So what you would actually need to do to observe this is use an instrument like TPFC to observe the planet, but to get any useful information from polarization, you really need to be able to follow the planet for a significant part of its phase cycle. So you can't just observe it when it's at its greatest distance from the star, which is what you might otherwise think of doing. You need to be able to follow it through a range of phases. So if you want to get the rainbow, you need to be able to look at this 40-degree phase angle here. If you want to see the glint, you're going to need to look at phases over here, crescent phases. And you can't always do this, because you may just not be lucky. If the orbit is face on, you don't get any range of phase angles. The planet just goes around the star and is always at 90 degrees phase angle. But for most cases, you should be able to reach the 40-degree phase angle. That requires that the inclination of the planet must be less than 50 degrees. And if they're randomly oriented, then about 64% of systems should be within that range. So it should be feasible for a large number of systems. But as the planet is going around the star, it's also changing in brightness quite a lot. And this is actually the light curve of Venus as a function of phase. So 0 degrees phase angle is full phase, it's fully illuminated. Down here is crescent phases. And this helps to see why glint observations are so difficult, because not that you would see glint from the case of Venus, but other planets are going to do similar things. Observing the glint means observing down here, where the planet is only about 10% of its maximum brightness. The Rayleigh scattering is a bit better. That's up here, about 30% of maximum brightness, and also where the planet is furthest from its star, so that's sort of an optimum time to observe. And the primary rainbow is up where the planet is really bright, although it is starting to get a bit nearer to the star. So this is just a picture of the optical system of TPFC, which is the sort of instrument we would want to use for such observations. And what I'm going to do here is just a quick comparison of what's involved in doing polarimetric observations compared with spectroscopic observations, which is the way people have normally been thought of characterizing planets. And what I've estimated here is that you would need to detect, for example, the rainbow signal and the Rayleigh scattering signal, you'd need to measure maybe 6 phase angles, and you'd need to measure the polarization of each one to an accuracy of about 2%, which would be sufficient to comfortably see these effects. And you can calculate that needs about 15,000 photons. And if you look at what's required for spectroscopic observations, capable of detecting the spectral features, similar calculation gives around 18,000 photons. So doing this is no more difficult than doing the spectroscopic observation. That doesn't mean it's easy. Both of these are really difficult things to do. But an important point is that you don't have to do one or the other. You can do both of these at the same time, because you can use an instrument that is measuring both polarization and spectroscopy. So it's not really increasing the time you need to characterize these planets, although it does mean you need to think a bit more about how you plan the observations. You can do both of these in principle with the same instrument. And in fact, the designs for TPFC already include splitting the light into 2 different polarization channels. I believe this is done in order to allow the coronographic systems to work optimally, but it essentially means that it's already got built into it the main instrumental requirement for being able to do polarization. Okay, so how do we follow up this work? We would like to get better observations of what's polarization phase curve the Earth actually produces. And there's a couple of ways you can do this. You can observe the lunar Earth shine. This is Earth light scattered off the dark side of the moon. And this technique's been used by a number of groups to look at the spectrum of the Earth from space. But in principle, you can look at polarization of the Earth in this way. And in fact, Ordwin Dolphus did this back in the 50s. He measured the polarization of this Earth shine, and he detected the Rayleigh scattering signal from the Earth. The reflection of the moon complicates things because that introduces polarization effects of its own. It actually reduces the polarization to about 1/3 of the original amount. And polarization observations are now being attempted of the Earth shine, particularly Eric Poller at in the Canary Islands. The IAC is looking at this. The other way you can do it is to observe the Earth from space. And there's been suggestions for simple space missions that would do this. A couple of these were discussed at the recent AbSciCon meeting by Nick Wolf and Maggie Turnbull. So one idea was to have something that would actually operate from the surface of the moon that the astronauts would take with them and point at the Earth. Or you can have a spacecraft in space near the moon looking back at the Earth. And then the other thing I'm looking at is improved modeling of the polarization effects. Most of the models I described earlier were only using single scattering models. But I have a radiative transfer model for planetary atmospheres that I use to produce planetary spectra, and that I've used successfully for modeling the spectra of Earth, Mars, Venus, and Titan, shown here. And I'm planning to incorporate polarization into this so that I have a model capable of predicting polarization of a planet at any wavelength. And this will enable accurate estimates of the rainbow and glint effects for a range of different possible extrasolar planets. So, polarization could provide important information about a planet's atmosphere, the presence or absence of clouds, cloud composition, the atmospheric pressure, and even the presence of surface oceans. Although this, I think, is currently difficult with a mission on the scale of TPFC. Probably needs an even bigger telescope than that. Polarimetric and spectroscopic techniques are complementary for planetary characterization. They give very different information about the planet. And the observations should be feasible with a mission like TPFC in similar integration times to spectroscopic observations. So the recommendations are that when the TPFC mission or something similar is continued, because that mission is effectively on hold, it's not funded at the moment, it must include polarimetry capabilities in the instrument design and observing plan, and polarization needs to be included in models for extrasolar planet atmospheres, such as those that the VPL team is working on. Now, do I have a bit of time to say a bit about the Hot Jupiter work? Okay. Yeah. So all I've said so far is about what we may be able to do way in the future with missions like TPF. But there is actually one type of planet that we might be able to detect polarization from now, and that's these Hot Jupiter type systems, where you have a planet orbiting very close to the star, a giant planet. And these are likely to be the brightest planets in scattered light, because they're big planets and they're very close to the star, so they're receiving a lot of light from the star. And the idea is that looking at the combined light of the star and the planet, light from the star is unpolarized, the planet's light might be polarized at a few percent, 10% or so, but it's only 1/10,000th of the total light of the system. If you look at the combined light and can measure the polarization accurately enough, should be able to see a polarization at a fractional level of something like 10 to the minus 5 or less, probably a few times 10 to the minus 6. And this was actually modeled by Seeger, Whitney, and Sasseloff in 2000, and they produced the sort of polarization curves you might expect to see from one of these planetary systems. And they concluded that the polarization signatures are well under the current limits of detectability, which are a few times 10 to the minus 4 in fractional polarization. And that was probably true for astronomical polarimeters that were available at the time. But we knew that it was possible to do polarization much better than that. In particular from the work of James Kemp, who'd developed polarimetric techniques using a device called a photoelastic modulator. And he'd actually measured the polarization of the sun at sensitivities of pops in 10 million. So together with the group at University of Hertfordshire, Jim Huff and Phil Lucas, we came up with a design for a polarimeter that could measure stellar polarizations to an accuracy of about 1 part in a million. And this is using these things called photoelastic modulators, which are polarization modulators where you have a piece of optical material and you make it oscillate at its natural frequency by piezo transducers attached to it, and it produces polarization modulations at high frequencies, 20 kilohertz in our case. And these devices have been used both in astronomy and in laboratory conditions for doing polarization with very high accuracy. So this is the schematic of the device we built. It has photoelastic modulators, a Wollaston prism which splits the light into two polarization beams, and the detectors are avalanche photodiodes. which we chose because they're linear up to very high photon rates. And to do polarization to this accuracy, to measure 10 to the minus 6 polarization effects, basically you need 10 to the 12 photons. So you need to work at very high photon levels. And so this is the instrument. It's just an aperture polarimeter, just measures the total polarization of a bright star. And this is the actual device, and the team sitting on the back of the William Herschel telescope, La Palma in the Canary Islands. And this is the sort of results that come out of it. This is looking at what we call the second stage chopping signal. So we modulate the light rapidly using the photoelastic modulator, but then we also rotate optical elements within the system to reverse the sign of that modulation every couple of minutes or so. So this square wave pattern is the polarized signal we're seeing from the two channels, the two avalanche photodiodes, and that first case is for a polarization of, I can't read that from here, but it's something like 10 to the minus 4. It's what would have been about the limit of what you could measure with previous astronomical instruments, and it gives a huge signal with our system. And then these are smaller polarizations, 20 times 10 to the minus 6 and 12 times 10 to the minus 6, that show we can fairly easily see polarizations at this 10 to the minus 6 level. We also have to remove telescope polarization, which we do by using the fact that it's an altazimuth telescope, and we can see and so the telescope tube rotates relative to the sky, so we observe at different hour angles. So we've observed a number of stars. This is a summary of the polarization data of bright stars, nearby bright stars. So most of the stars, and the size of the disk here is a measure of the polarization. So these big ones here are about 200 times 10 to the minus 6. So we measure everything in units of 10 to the minus 6. So these are, what we're seeing up here is a region where we're getting far enough out to see interstellar polarization effects, to see interstellar dust. But most of these other stars have very low polarizations, except for a couple of cases which we think have intrinsic polarization. Regulus is actually a rapidly rotating flattened star, and Vega has a dust disk around it, so they're both cases that are probably producing polarization.
Where does the sun come in on there?
The sun, well, it's not on the diagram, but it would be it's less than 10 to the minus 6, so it would be the smallest dots on there. Okay, well, the basic result so far is that we've looked at one of these Jupiter systems, and we've failed to detect the polarization signature that was predicted. But we probably chose a star which was not the best one for a number of reasons. So we're continuing observations of other systems. And we have found various other interesting things. We found that, for example, normal nearby stars have very low polarization, which is helpful for detecting the effects we're looking at. We don't yet see the expected polarization signature of a hot Jupiter planet, but we may be able to do so by looking at other systems. We've also discovered interesting things about polarization effects in the Earth's atmosphere. At the La Palma site frequently gets Saharan dust blowing over, and we found that Saharan dust produces lots of polarization at the levels we're looking at, which actually tells us interesting things about how dust particles behave in the Earth's atmosphere, because it implies they must be oriented in some way. Okay, finish there.
It seems like you could use the requirement of having the correct phase angle to actually calculate the angle of inclination. Is that something worthwhile? Have you thought about that?
Which are you talking about, the hot Jupiters or the...
Oh, sorry, the planet.
But yeah.
For example, the required phase angle of glint you could maybe use to figure out the inclination between the planet's orbit and the star, which...
I don't know if the glint tells you that, but polarization angles in general will do that, because the polarization tells you the vector to the star, effectively. Polarization is always orthogonal to the star's vector, so if you can see how that rotates around the orbit, you can get the inclination out of it.
I'm curious as to if the glint can allow you to distinguish between water, ice, or some other liquid. If there's a characteristic to the glint, it will tell you what it's actually glinting off of.
I don't think you can easily tell that. All you can tell is that you've got a reflecting surface, and I think you probably have to figure out from other properties of the atmosphere what that is likely to be. So I guess other information on the atmosphere should tell you the chance of having a liquid water ocean or some other liquid.
Tao Bu, can you just say a little bit more? How long did you look at it? So can you just describe the observations, and how far below did you go in the predictions and so forth?
Well, this is what we're seeing for Tao Bu. Okay, so we got reasonable coverage of the phase, although there's a few gaps. And we did seem to see some polarization, but the curve is completely wrong for what we would expect. If it was a clear atmosphere, for example, we'd expect peak polarization to be around 90 degrees, which is probably where we're seeing low polarizations. We seem to be seeing high polarizations here, where we wouldn't expect to see much polarization. So we don't really know what's going on, but what we suspect is that what we're seeing is probably not due to the planet. It's probably due to what's going on the star, because that's consistent with what's come out of the Canadian MOST satellite has been observing this thing as well, looking for the light curve that you'd expect from scanning off the planet, and they don't see anything like that, but they do see bigger effects which they think are coming from the star. We also know this star is magnetically active, which means there might be some polarization coming from magnetic Zeeman effects and so on that might be confusing us.
But is each of these data points just looking once, or did you have many times?
We followed it over, well, several cycles, but with incomplete coverage on all of them, because we missed. Well, you missed the daytime part anyway. The period's only 3-point-something days, and we generally missed some bits due to cloud as well. So,
right. So
put together from several
it's
cycles.
not really from a Fourier analysis of lots of data.
It's a few cycles.
Pardon?
It's a few cycles, not many. Yeah.
But each data point is plotted there, though.
Yes.
Yeah.
Excuse me. Those sorry. The TPF integration times you were talking about there, I think are around on the order of a week or two. So I was wondering, to get 18,000 photon or whatever you needed.
Yes,
I was wondering about the effects
long.
for something like Earth, which has both these water and cloud systems, and it's going to be, but also land. How much is the rotation of the planet in that 10 days, if you will, going to smear out some of these polarizations?
It's obviously going to have some effect. Yeah, I mean, well, not just the rotation, but the fact that the cloud cover is changing all the time. I think these are on the whole big enough. Certainly the rainbows and the Rayleigh scattering effects are big enough that they should show up. I'm not so sure about glint. I mean, obviously the glint spot can disappear completely if a cloud forms over it.
Or a continent.
Yes. So, but I mean, Enric Pola has been looking to see if he can see the rotation of the Earth in the Earthshine data, and I think he's found it quite difficult to pick it out. So the rotation effect doesn't seem to be that huge.
So I was talking to Bill Sparks at the AppSciCon,
Yep.
and he's interested in looking at being able to detect various color that might be involved in photosynthesis, and not just green plants, but perhaps red plants. And is there a possibility of using polarization then to not necessarily look at color from photosynthesis, color that might be associated with a chemical signal organic or inorganic signal. For example, the dark coloration on the leaves of Europa, for example, could that be detected with polarization? And could we actually find a way to delineate what makes up some of that dark coloration?
Well, I mean, the reason Bill Sparks is able to detect polarization signatures is because these are chiral molecules. So things like chlorophylls do produce a circular polarization signature. So
There's a whole range of organic.
in principle, any organic molecule will do that, but in most molecules, the circular dichroism effects are more in the UV. So you might have to go far into the UV to see strong effects. But all of these are very small signals. I mean, the effects Bill is seeing is sort of 0.2% polarization at best. So we're looking for something sort of 100 times down on the sort of atmospheric polarizations I'm talking about here. So yes, I mean, if you're looking at things in the solar system, it could certainly be feasible.
Is there a future for making this technique more sensitive than it is right now? Is there a mechanism to make it 100 times more sensitive than it is now?
Well, if we're talking about exoplanets, the way you make it 100 times more sensitive is make your telescope 100 times bigger. If you're talking about looking for things in the solar system, then I guess we ought to be able to push circular polarization measurements down to these sort of 10 to the minus 6 levels we're achieving with planet pole principle, which is better than anybody's actually used in any solar system observations so far.
How much you showed the plots that show basically the peak migrating at a single wavelength, if I understood correctly, with the different compositions. How much additional diagnostic information do you get by looking at the migration of a peak, sort of spectrally?
The rainbow peak.
Yeah, essentially
Yeah.
the rainbow peak. Yeah. If you're looking at different wavelengths, does it buy you a whole lot more diagnostic?
Yes, it does help a bit because you get not just the refractive index at one wavelength, but you get part of the refractive index curve as a function of wavelength. And James Hansen actually used that in the Venus rainbow measurements. That was part of the information that tied it down to sulfuric acid.
So if you want to verify this for the Earth, the polarization, why can't you use a satellite that stays pretty close to the Earth? Like, why do you have to get so far away? Couldn't you just kind of stare at the ground at different angles and get all the information you need?
Well, effectively, we have that sort of information from Polar, so we know these polarization effects are there. In principle, I guess you could try and use a whole lot of satellite data and combine it together to get some idea of what the total Earth signal would look like. But you don't usually get quite the same thing because, for example, the satellites usually look straight down, whereas if you're actually looking at the integrated view of the Earth from a distance, you're looking straight down in the center of the planet and you're looking at different angles as you go to near the limb. But there certainly may be some potential for using existing satellite data to get some of this information.
I mean, if you just convince them to not look straight down, convince them to like look at the edge, look towards the horizon.
Yeah, there are certainly possibilities there.
Any questions? No. Okay. Okay, let's thank Jeremy again.